We are now in section 4.2 and the title is the Mean Value Theorem. Right? We begin with Theorem 3. Theorem 3, Rawls Theorem. Suppose that y is a function that is continuous at every point in the closed interval. So that's just saying if y is continuous on a closed interval. And another condition is that if, when you say suppose, it's the same as if the function is differentiable, so it has a derivative at every point in the interior. See, that's just the interior, all right, AB. So that's why you have an open interval, because now it's you don't include the endpoints. You're just saying it's differentiable at every point between A and B. Now, it says here, again, another condition, if f of A is equal to f of B, so they have the same y value basically at the endpoints. Then it says there, then there is at least, that's another important thing, at least, so that means it could be more than one, at least a number c in AB at which its derivative is equal to 0. Now let's just interpret for a moment what it is graphically, right? So you've got a function that's continuous on a closed interval. Right? So let's say this is from A to B. You've got a continuous function. Right? Now why did I do this? How come I did this? Because it says it's continuous from A to B, and not only that, the f of A is equal to f of B. F of A, which is also equal to f of B. Now, what is the conclusion? And then you see that how you have a smooth curve in between A and B. That's the way we say it's differentiable at every point in the interior. Now, that's this condition. It says then, what is the conclusion? There is at least one number C. So let's say that's your number C, at which its derivative at that point is 0, which, look, right about there. Okay, so that's what Rawls theorem tells you. You have a continuous function and differentiable in the interior. You are bound to get a number C whose derivative is at the slope of the line tangent to the curve is 0. Let's do another curve. And say here is right, and suppose we are concerned about, say, here's A, say here's B. Now when you say that f of A is equal to f of B, you can draw a horizontal line through it, and there's your f of B, and there's your f of A. When they're equal to each other, in between that smoothness of the curve, you are bound to get at least one. So C1, C2, C3, whose derivative of the line tangent to the curve will be parallel to this line. So that's right there. Okay, because it has to make sense that if this meets another, will have the same y value right there, it has to either go down, up, to make it back to that y value. And that's why you get these lines tangent to the curve that are 0 slope. All right? So again, you can have one or more than one, like this example. Here is just a nicer picture where you have one interior point, and again, it's just these two lines are parallel. You have the y values are equal at A and B. So eventually, because they're equal, somewhere between that, there has to be a line tangent to the curve that's horizontal. And here you have C1, C2, C3, where you have 0 slopes. Okay? So you have one or more than one. That's what this figure is telling us. But again, the Rawls theorem conditions are that it's continuous on a closed interval, differentiable on the interior point, then you're guaranteed. You're guaranteed to get at least one of these C's where you have a zero slope. Well, what are these new figures that we have here? Well, it says here that there may be no horizontal tangent if what? If the hypotheses of Rawls theorem are not satisfied. Now, what do they want? It has to be continuous on the closed interval. See, this is not continuous on A from A to B. So even if you have that saying f of A is equal to f of B, but it's not continuous, then you won't get a flattened slope. Here, again, it's discontinuous in the interior point, so even if you satisfy that part, but because it's discontinuous, problem again. Now here, what about this one? It is continuous, but what is the condition that's not satisfied? It's not differentiable at x0 because you've got a line tangent to the curve that is vertical. So then you won't have it won't satisfy the conclusion of the Rawls theorem in any of these three because the conditions are not satisfied. So what are the conditions? Let's remember. Continuous on a closed interval AB, differentiable on the interior, okay, interior, and then f of A equals f of B. And what is the conclusion? So if these are satisfied, then what? Then you are bound, okay? You're bound to find, then we can find an interior C. So that means it's contained. It has to be between A and B, where we can find an interior point such that what will it do? The slope of the line tangent to the curve at C is 0. You have a horizontal tangent line. Now we turn to the mean value theorem. This is just an extension of the Rawls theorem, because the Rawls theorem says that you have a continuous function, okay, and you've got the same y values, and naturally if they're the same, right, you're going to find a C in the interior with the same slope. Okay, what is mean value theorem? Let's see what this says. Suppose y is continuous, you see the same condition on a closed interval AB, and then it's also differentiable on the interior points of AB. So it's the same things that satisfy, the same two things that satisfy the Rawls theorem, but we have one more. It says there, if that's the case, then there is at least one. So again, you can have more than one. At least one C in the interior at which, okay, f of B minus f of A divided by B minus A is equal to the slope of the line tangent to the curve at C. So the question is, what is this other side of the equation? Okay, let's see. It's easier if we graph it, right? So f is continuous on a closed interval, differentiable. That means it's smooth, no corners, no cusp in the interior. Then you have at least one point such that, right, the slope of the line tangent to the curve at C will coincide with the line secant to the curve between A and B. So let's draw a curve there, okay, and that's from A to B. Now the question, is it a continuous function? Yes. And then we can see that it is nice and smooth. So in the interior we have no problem taking its derivative. That means all the derivatives exist because you don't have any sharp corners, basically. Then it says there is at least one point C in between A and B, such that, okay, this is the slope of the line tangent to the curve. It'll be equal to the secant line, the slope of the secant line. Now, what is the slope of the secant line? Well, here is your f of A, and that's your f of B. Now, what is the slope of the blue line, the secant line? That's the slope of the secant line. The slope of the secant line, which is your blue curve. And then it says here, you're guaranteed, by the mean value theorem, you're guaranteed that between A and B, you'll find at least one C. So let's just say these are one of the C's and another one right there. Where it says that they will match up, it's parallel to the secant line. So what is this? It will have, the slope would be slope of the tangent. The slope of the tangent, okay, will be equal to the slope of the secant line. All right, so what is this? That's f prime of C1, and you've got here f prime of C2, and it's equal to the slope of the secant line. And what is this slope? Well, y2 minus y1 divided by x2 minus x1. So that's the slope of, you've got f of B minus f of A divided by B minus A. All right? So that's all the mean value theorem says. But these are the conditions. You've got a continuous function in a closed interval. It's differentiable on the interior. And then you'll guarantee to find at least one point in the interior such that they will have the same slope of the secant line. All right? And they'll have to be parallel. This means that the slope of the line tangent to the curve at C is equal to the slope of the secant line. All right, here is an example that satisfies the hypotheses of the mean value theorem. And in fact, it's actually the Rawls theorem because it just so happened that, you know, they have the same values at the end point. But let's see why it satisfies. Well, you have a continuous function. It's a semicircle. It just kind of not proportional right now, but it is a semicircle centered at 0, 0 and radius 1. And we have a continuous function on a closed interval. Okay? And then, is it differentiable? Yes, it's differentiable in the interior, but not at the endpoints. Okay? Let's see why. What is y? It's equal to 1 minus x squared raised to a half. Okay, the square root is 1 minus x squared raised to a half. And then you're looking at the interior. I mean, let's now take its derivative. The derivative is 1/2, 1 minus x squared raised to a negative 1/2, multiplied by the derivative of the inside is negative 2x. Again, chain rule. So if you rewrite everything, and that gets canceled out, you see that? So now we've got the negative of x over the square root of 1 minus x squared. So what did we do? We took the derivative, and then the next thing we'll do is set it equal to, let's see, let's take y of negative 1, which is the square root of 1 minus negative 1 squared, and that's just equal to 0. Y of 1 is the square root of 1 minus 1 squared, and that's 0. Okay? So now the thing that we do is this is your f of a, okay? This is f of a, this is f of b. So we're guaranteed that between -1 and 1, you're bound to find an x equal to, in this particular case, it's equal to 0, where you see how the slope of the line secant, the joining these two, just turns out that it's a horizontal line, and you've got a line tangent to the curve at x equal to 0. And later on, I'll show you step by step of how we find these points, the interior points. Okay, one more thing that we look at here is that, right, in this function, if you set that equal to 0, right, set that equal to 0, that means x is equal to 0 will make the derivative 0, and when you have x equal to -1 and 1, the function is not defined. I mean, the derivative is not defined at -1 and 1 because that will make the denominator 0. So in this case, you have lines tangent to the curve that are vertical on the endpoints, so it's not differentiable at the endpoints, but it's differentiable everywhere. See, anywhere between -1 and 1, this whole function is defined. So we can just say it's differentiable in the interior -1 to 1, but not at the endpoints. Not at the endpoints.